Well, hello there. Welcome to another problem session. So today we have a circuit that is neither parallel nor in series. So this kind of circuits go by the name of bridge circuits, and kind of looks like a bridge. So you can see that if this was not there, if this part was not connected, then over here when the current comes in and splits and goes through the top and then come back and then combines, so this will be a parallel part if this thing was not there. Because this is here, you can see if this current, say this is I, and it goes towards this I1 and through this is I2, then over here now is kind of split, or over here is split. So I1, say over here comes in I1, then suppose it goes this way. I don't know it goes this way or that way, but let's call it we'll call it I5. We'll give this a name I5 just to be consistent with all these numbers I've used for resistors. Then I5 comes in here and I2 combines, and this is I3 now. And when it comes in, I3 will combine with I4. So over here, I1 comes in, some of it goes through here and some goes through here. That I'm going to call it I4. So you can see over there the split is I1, I2. Over here, combine is I4, I3. It's still I. So this is not a parallel circuit. If it's parallel, then over here it will be I1 and I2. So it will be I1 again and I2 again if it's parallel. But it's not parallel, so it can be is something else. Okay. So we are going to study it the way we learned. So basic things we learned is to basic laws. Let's write over here Ohm's law. So if there is a one end of let's call it A and a B end, and this side is VA and this side is V potential values, and this is resistance R, then the current, if this is bigger than that, the current will flow in that direction. And so this is VA minus VB equals I times R. And if this was bigger, then this will come out negative, meaning direction is opposite. So that's one law. This is Ohm's law. And in the voltage, if you have a battery, so if this is voltage is labeled as a V0, that means if it's a, let's call it C and D, then VC minus VD is V0. So this is the and this is if it's a battery, then it's a DC, and it's a for a steady current situation, current will always flow this way inside the battery and outside the wire, and this voltage will be bigger than by convention. Right, so it's 12, then this will be 12. So these are the basic rules we're going to use. One other rule is at anywhere in the circuit, at any one point in circuit, V at that point will be set to be 0. Say point P. At one point I can set it, not more than 1 point. Okay, so that would be like a reference. This is reference, zero reference for the potential, also called ground. Zero reference or ground. So there can be only one ground and not more than one ground. You're allowed to set. Okay, we try to figure out if I can find all the V's, definitely I can find all the I's. So that's our approach here. We're going to find the voltage first, and then we're going to find the current from there. So how do I set it up? Well, let's see. We are going to label points. So all these points are going to be on one potential, and that's going to call point A, and all these points on the other side till I hit a resistor. So these are just connecting wires, and we are assuming there are no resistances in them, so we'll call that point B. So at one point I'm supposed to set 0, so I'll just say VB is 0. So we're going to choose VB equal to 0. So this is known, and then that makes VA equals to, that means VA is simply 12 volt, because VA minus VB is 12. That makes it, with that, okay, this is 12. So that's, we know. And then I go over here, and then this is one point is all on this side. All this point will be, let's call this C. So the VC is unknown, and all this point register, that's this point, these points over there, let's call it D. Then VD we don't know, and over here we don't know. These are the unique points, VE. So VE we don't know. So this will be a 3 unknown problem. So if we solve this, we should be able to get it. So for each one of the situations, we already used up this by using that. So for each one of the registers, we are going to set it up. So this is I1. So VA minus VC equals I1 R1, and that's VA is 12 minus VC equals to I1 is unknown times 1. And then for this register, VA minus V sub D is I2 R2, and that just will give me 12 minus V sub D equals to 2I2. And we so with that one, we use that one. Let's use I5. I5 will be VC minus VD. So I must keep the direction that I picked. Okay, so I5 R5, and that's don't know, VC VD not known, so VC minus VD is equal to 5 times I5. And then let's do this one, VC minus VE, neither of them are known, I4 R4, and that just gives me VC minus VE equals to 4I4. And then the last one is VD minus VE equals to I3 R3, and this gives me VC minus VD, this VD minus VE, so VD minus VE equals to 3I3. And then we've got the last one is from here to here is VE minus VB equals to, and this is I, so this is gonna go, I will go through this, not splitting. So this is I times R, let's call it R6, and that just gives me VE, because VB is set to be 0, so this is set to be 0. So VE equals to 6I. Another thing I notice is over here is splitting, so we have a I equals to I1 plus I2, and then over here I1 comes in and splits into I3 plus I4. So this is a current conservation, and over here you have a I3 is equal to I2 comes in and I5 comes in. So these are coming in, so they must add up. I2 comes in. And then over here, we have these guys come in. I must equal to I3 plus I4. So these, if I put in here, I'm going to get equations for the unknown. So I'm going to now pause this video and kind of put these equations in here to get equation unknowns be 3V's, okay? So what I did was I solved these for I's in terms of V's, and then I took them and plugged them into these guys, and so I got equations for all the V's. Those are the unknowns, the way I'm solving it. There's other ways of solving it, right? I will illustrate another way of solving for currents if this was the only thing I wanted. So this is either a solve for currents or solve voltage, but they're equivalent. So in the voltage approach, you just set up equations. So I got 4 equations here, but there are only 3 unknowns. But let's simplify it. When I simplify, I got so these equations then turn into 4 equations. So this is like 1, and this is 2, and this is 3, and this is 4. So these 4 equations simplified this way. I want to make sure that they're consistent. Sometimes you can make an algebra. Actually, I did make a little algebra error when I'm transferring, so I caught it. I found that you can add these guys and take that away, then you get a 0 on this side. Then these guys all should be consistent, and actually 4 is nothing but combination of 1, 2, and 3, linear combination of 1, 2, and 3. So it's not an independent equation, and we can just kind of ignore one of these. Maybe say you ignore one, say ignore that, and solve this simultaneously. So you can do a number of ways. You can do a matrix method or elimination method or whatever. So suppose I want to do matrix method, then you'll have some A and some vector V equals to some vector B. And what that is let me write that down. A will be all the coefficients, and V will be just VC, VD, VE, these 3 unknowns, and B will be this constant on the other side, so 18 and 12 and 6, and A will be like these numbers that go over here, 0, half, 1/6, and then you'll have this number go over there. Let's call it A. That's A, and then this minus 1/5, and this is minus 1/4, and this is minus 1/5, and this is I'm gonna call this C, and this is minus 1/3. So we have that. So we have equation AV equals to B, and because these rows are all independent, we have actually full degrees of freedom here. So V is going to be, there will be inverse of this matrix B, and so when you multiply this inverse, and that's your read of the answers. V, it will come out to be 3 numbers, and these numbers will be correspond to those numbers. So you have a VC, VD, and VE. These will be found. Once you find them, you just plug into these guys and plug into these guys, and then all the currents are obtained. So once you find the currents, to answer this is very easy. Power consumed will be the power that got supplied by this. And if you know the current that's going through that is this guy, and then the voltage. So this will be, the answer for this is very simple. The current and voltage multiplication at the battery. Okay, so that's really a lot of algebra here, and sometimes it's interesting to do them. Okay, if you haven't subscribed yet, please subscribe, and if you like this explanation, you learned something from it, you can hit the like button, and you can also check out my website where I have the entire textbook out there. Okay, so there's an alternative method I want to illustrate to you that's often is in the books, and it's just going after the current directly. Okay, so I wanted to do it for current directly. So how would I go about it? So usually you use what is called Kirchhoff's rules, and they're basically based on A, B, and R. You have I, so VA minus VB equals IR, and so at any point the potentials, say this is CD, so VC minus VD equals V0. So these are two basic rules, basic laws, so to say, and at any point the potential is unique once you set this to be 0. So it leads to two rules. There's a at any junction, if the currents are coming in and some currents are going out, so at any junction the sum of all the currents should be 0. So sum of all the currents equal to 0 at any junction. So in is positive and out is negative. So that's how it, so if this was 1, I1, I2, I3, I4, I5, so this will be I1 plus I2, they're coming in and these are going out, so I'll just use like this, minus I3, I4, I5 equals 0. So this junction will give me a relation between that. We have already used that. It comes from conservation of charge and no building up. So this is steady currents, so there's no building up. This current not just disappearing over there. And if you go in a loop, so you start from A, so if I and this is B and this C, so that these 3 points, right, these are all one potential, this is all one potential, this is one all potential. So if I go around, I'm going to get so if I go from here to here and changes VB minus VA, and then I go from here to here, this is changes VB minus VA, or you can say VA minus VB if you like, and then I'm going the same direction. I'm going to VB minus VC. So whatever there is, VA minus VB, and this current is say I1, and this current says I2, this current is I3, like those directions. So voltage dropped here, VA was greater than VB, and that dropped by I1 times say R1, and this is R2, this is R3, R1, and VB minus VC is I2, R2, and then when I go a drop here, I'm going in the direction of the current, so I'm going to drop voltage, VC minus VA equals I3, R3. So whenever I'm going in the direction of the current, voltage will drop. Assumption is that this is higher voltage than that. So if I add these up, so in a loop, this side goes to 0. So it is sum of this IR values. and as I'm going in the direction of the current. So this is often confusing. This is a very useful rule, Kirchhoff rule. But suppose if I had drawn and the current I1 was going this way, and this is A, this is B, this is C, and this was going this way, I2 was going this way, and I3 was going this way. So if I do it like this now, I would actually get VA minus VB equals to, assuming that this is bigger than that, if I'm going that way. So it's going to be minus I1 R1, not plus I1 R1. So that's how it, but the other guys will be same, because I'm going to go in that direction, in this direction of the current. Again, the direction of the current. This one I was going in the opposite direction of the current, so I pick a minus sign here. When I add this up, now I'm going to get a 0 on the left side, as these guys will cancel out. But I'm going to get a minus I1 R1 plus I2 R2 plus I3 R3. While over here I got I1 R1 plus I2 R2 plus I3 R3. So now we use these, then we can get another set of equations to solve. Okay, and they're equivalent, and they're not like less work. They're just another way of doing the same thing. So let's just work it out. So we'll have some junction equations. So you have one junction here, one junction here. There are two junctions the currents are coming in. So you have a junction equations. So we have I equals to I1 plus I2. And actually there are more junctions. There's this junction and there's this junction. And then over there I1 is equals to I4 plus I. These are the same as before, right? I4 plus I5. And I2 comes in and I5 comes in, I5 comes in, but I3 goes out. And over here, I4 comes in, I3 comes in, gives me I. And you can see that one of them is definitely redundant. So this is not all one redundant. Okay, so those junctions, in case of loop, you can have, let's see, one loop, you can immediately see I can go this way, we can go this way, and another loop can be like I go all the way like this. So you can have a 3 loop equations, and say this is loop 1. So I'm going in the same direction of the current, so minus I1 R1. Over here I'm going to the same direction as current, minus I2 I5 R5. And over here, while the current is assumed to go in that direction, but I'm going in the opposite direction, so I'm going to pick up voltage, which is I3 R3, and I came back to the same place. So this is came back to that place. So that's going to be 0. Oh, I didn't go there. I2 R2. I went here, not there. I'm in this loop. So that's one equation. And then if I go in here, I go minus I4 R4. I go in that direction, so I drop the voltage. And then I go opposite direction, I'm going to pick up the voltage. I3 R3. I go opposite direction, so pick up the voltage. I5 R5. But I came back to the same place. So I start from, say, C and came back to C. So this equation 2. And this one, say start from B. So I pick a voltage. So I pick 12 volt, a B to A, and then A to D. I'm going the same direction as the current, so minus I to R2. And again, I'm going the same direction this, minus I3 R3. I'm going the same direction the presumed, so minus I times R6. And I came back to B, and that's equal to 0. So these are the equations. Now you have to solve for, you set it up and solve for the unknowns in the equation. So eliminate all the redundant things, and then you will be left with 3 unknowns, and then you're going to solve them. Okay, so I'm not going to go and do this algebra for you. I just wanted to make sure you know that there are other ways of solving this problem, and a lot of people prefer this way, but I prefer the voltage way because it's kind of very simple, and I can keep track of the unknowns better. That's just my preference. Whichever you like more, you just go ahead and follow that. But ultimately the basic rules are this Ohm's law, and that in voltage is like that. And the third rule will be at one point. So this is rule 1, rule 2, rule 3 will be at one point in circuit, you can choose voltage at that point to be 0. That's the choice of ground, just one point. You can't just willy-nilly set everywhere. So if I had a, say, if I had a like this kind of circuit, now you have 2 batteries. You have a 12 volt and say 9 volt. You can set this point to be, let's call it A. So this is all A, and this point B, this point C, and this all point is D, and this E. So you can set VA equal to 0, but VB not 0. You can't set this also 0. Okay, just because our VB A, B, C, or this is negative of that, so VC is not 0, so you can't set that. You can have that combination, or you can have a VA not 0 but VC equal to 0. So you can have this or that, but you can't have VA equal to 0 and VC equal to 0. You can't have that. Okay, so make sure that you can only pick one place 0. With that, I'm going to stop, and I hope you enjoyed it. Take care. Bye.